All right, so to start things off, this last unit, we're going to talk about parametrics and vectors. Maybe you've heard of vectors before from physics. And then we're going to get into some polar equations. We're basically going to talk about new equations that we're not really familiar with, because parametrics and polars are not graphed the same way typical equations you're used to are graphed. We know, like from algebra or pre-calculus, you normally graph a function using the xy coordinate system. Parametrics and polars don't necessarily use that same xy method, going left or right or up and down. So we're going to practice utilizing our calculator in some capacity to graph these parametric equations. Now, parametrics are normally two different functions. One is an x function, one is a y function. And notice how the variable in each of those is t, which is normally representing some time amount. What parametrics do is they give you a way to analyze, like if you think about particle motion for a moment, how the x coordinate is changing independently from the y coordinate. So at any point in time, you could plug in that value here and you would know kind of your x distance, and you could plug in that time here and you would know your y distance or y value. Okay, so we're separating, instead of having an x and a y in one equation, we now have an x and a y in two separate equations. One's representing an x horizontal distance and the other is a y vertical distance. So without a calculator, we're going to try to make a table and then sketch it. And based off of us sketching it, we should be able to determine the direction of the graph, like which direction a particle is moving. And then we'll try to verify it on our calculator just to make sure we did everything correctly. Okay, so in terms of our table, we have three variables to consider. We have t, x, and y. Bless you. And we specifically want time values from -2 to 3, so maybe we'll just count by ones. All right, so at those individual times, we'll plug in those t values into the x equation and the y equation to get our x location and y location. So for instance, if you plug in -2 into the x equation for t, you'll get 0. And if you plug in -2 for the y equation for t, you'll get -1. We're just going to repeat the process for the other t values. Can we get those values? Okay, so now that we have an x and a y value for each particular moment in time, we're going to graph those x and y values on a typical coordinate system. So it looks like our x's have to go all the way out to 5, at least based on our table, and then out to -4. And the y values go, I guess, down to -1, but then all the way up to 1.5. All right, so if we plot our first coordinate, 0, -1, we would be right here. So that's kind of where we start at time -2. And then 1 second later, at time -1, we're at the coordinate -3, -1/2. So somewhere right there. At time 0, another second later, we're at -4, 0. Another second later, we're at -3, 1.5. At time 2, we're at 0, 1. And then at time 3, we're at 5, 1.5. So if you kind of think of this almost like an aerial view, like from a helicopter or a plane, this is where you're starting at time -2, and then this is where you're located 1 second later, this is where you're located 1 second later, this is where you're located 1 second later. So it's like you're looking at maybe an ant colony or some aerial view watching the path of some object that's moving. So here's a curve in some capacity. We didn't connect the dots just yet, but we also need to indicate the direction of the path. So if we were to connect all these dots, it would look something like that. And since we know a specific beginning point and other points throughout time, we might be able to signify the direction using some arrows. Right. So we're going to skip down a little bit and actually fill in these blanks, and then we'll get back to this problem. How parametrics are different from a typical coordinate system. Okay, a regular coordinate system, let's see, parametrics equations, not only do they show the path of the object, but they also show the direction in which an object is traveling, and we'll fill in the last one in a second after we explore the other two examples. So the other thing we want to do for this one is eliminate the parameter. Now in this case, the parameter is that variable t, that extra variable in this instance that we're not really used to seeing. So what we're going to try to do is turn these two parametric equations into one, what's referred to as a rectangular equation, something we're used to with just x's and y's. So can you think about how we can kind of merge those two equations together by getting rid of or eliminating that t? Yeah. There we go. We're going to use a system of equations. So between the two equations, which one do you think is easier to get t all by itself? Y. The y. Okay, so if we get t all by itself, we'd have to multiply the 2 over. And now that we know what t is in terms of y, we can substitute 2y into the t in the other equation. Notice how we eliminated the parameter. We got rid of that variable t, and we have one equation with an x and a y in it. The only thing is we're not used to seeing an x equals equation, so we're eventually going to rearrange this to get y all by itself. So if we square this, we'll have 4y squared. And then we can go ahead and solve for y. Maybe add the 4 over. We can divide the 4. And then we'll square root both sides. So we'd have plus or minus the square root of 1/4 x plus 1. All right. So if you were to actually graph the positive square root function and the negative square root function, it should look something like this particular section of graph that we drew on our paper. So let's just go ahead and check that real quick. So on your calculator, if you hit y equals, we'll type in the square root of 0.25x plus 1, and then in y2 we'll do the negative square root of 0.25x plus 1. let's see, we said our window on our paper was -4 to 5, counting by ones. And on the x-axis, I think we did, what, like -2 to +2, counting by ones? So doesn't that look like the shape of the graph we drew? We just drew a particular chunk of that graph. You see how it matches? Pretty darn close, right? Okay, now there's actually a way on your calculator for you to graph the parametrics instead of having to go through this eliminating the parameter process. And that's what we're going to kind of do mostly today. So on your calculator, can you hit the mode button for a second? We're used to going here to checking if we're in radian or degree mode, but if you go to the next line down, normally function is highlighted, that F-U-N-C. The next equation is, or the next option is par for parametrics. So I want you to hit enter on that one. Okay, the next one is POL, that's short for polar. We'll get to that later in this unit, but let's go ahead and select parametrics. Now go ahead and hit Y equals again. Do you see how that menu changed? It doesn't say Y1, Y2, Y3 anymore. It says X1, Y1. So when you're in parametric mode, you can go ahead and type in your X equation and Y equation. Our X equation was T. Where's the T button on your calculator? Right, okay, so this button right here that we normally use for X, the order of those variables is the order of the option for either function, which is X, parametric, which is T, and then theta is actually going to be polar when we get to that later. So we'll type in T squared minus 4, and our Y equation, yeah?
How come it still only graphs half the graph?
It only what?
It still only graphs the top portion of the graph. Why is that?
We're going to go to window. We might have to change some things there, okay? And our Y equation was Y over 2, okay? Let's go ahead and go to window. When you hit window, notice how the T-min, T-max, and T-step are listed. Those are new, right? The X-min and X-max are going to be the same. Now, the T's, we're going to utilize the interval that they give us here. So the T-min would be -2. The T-max will be 3. And the T-step is the interval of how you want to count from -4 to 3. So do you want to count by ones? Let's kind of play around with this for a little bit. If we go ahead and just type in 1, let's notice what happens to the graph. You see how it kind of looks fairly jagged and it graphed it pretty quickly? That's because your calculator is only plotting 1, 2, 3, 4, 5, 6 points. It's only plotting the 6 that we did by hand. If you go back to window and change the T-step to 0.1 and hit graph, it still graphed it fairly quickly, but it wasn't as quick as the previous one because your calculator is graphing more ordered pairs or points to plot. Maybe we want to change it to 0.01. Notice how much slower it takes to graph it because it's graphing many, many, many more data points. So maybe the reason you didn't see the whole thing was because your T's were set differently. Eric, is it working better now? Okay. Okay, so we're going to utilize parametric mode for this section. For Y1, when you hit that, or Y equals, we should be able to type in both functions. And for the window, you're going to have to go ahead and type in how you want to count for your T's or your time. Okay, so let's go ahead and try this next one. Okay, so we're going to go ahead and graph this function in Y1 and this function in Y2, or sorry, X sub 1, Y sub 1. I'm used to saying Y1, Y2. And then we'll utilize this time interval. So we'll have 4t squared minus 4, and then t. Our window for the t's will be -1 to 1.5. And maybe we'll use, what do you want your t-step to be? 0.01? That's fine? Okay. Go ahead and hit graph. What do you notice? Isn't it the same picture we had before? Right? But didn't this one graph faster than the other one, even though like the t-steps were the same? Right? Okay, so what do you notice about those graph, or the graph? We can say same graph, but faster. Okay, because we had the same t-step for both of them, but this one, the calculator was able to graph more quickly. Let's go ahead and try the other set.
But our table values for it are different, so how can we do the exact same graph?
So the table values are different for the different times. So what's happening is you're still landing on the same spots, but you're just at a different spot for a different time. So for instance, we started here for this graph,
Yes.
but we might be starting somewhere different for this one. It's just, we're still here, maybe just not at time -2.
But even if I took that parametric graph
Mm-hmm.
and I plotted the same points for t that we did on the other one,
Yeah.
the points come out differently. So for example, -2, y is -2, or for t -2,
Uh-huh.
y is -2, whereas for t -2 on top of y was -1. So how can we do the same graph?
Notice how we changed the function though. We multiplied this one by 4, whereas this one wasn't.
I
And
understand
you understand that? Okay.
why they're different, but I think you just said that they're the same graph though, right?
Yeah, they're the exact same graph.
But they have different y and x values. Are you just talking about the shape? You're not talking about the physical coordinates?
I'm talking about the same shape. Sorry. Yeah. Same physical or same shape, but it just was able to graph it faster.
Okay.
Okay. Let's go ahead and try the next one. So we'll type in 4 parenthesis 2 sine t plus 1. All right, and then our window will -1.571 to 0.253, and maybe we'll leave the same t-step. All right, notice how that one happens to also be the same graph, okay, graph shape, but in terms of the previous one, it didn't really graph as fast. So apparently the t-step in this case is significant because we're graphing more data points than we did perhaps for previous ones. So what's interesting about these parametric equations is that they show the path and the direction of the object, but they also are signifying or showing some type of speed, like how fast it's traveling along that path. So while typical like x and y coordinate equations, they don't really show, they might show the path of the object, but parametric equations also show the direction, and they can also signify the speed, depending on how fast your calculator can graph it. Okay, so we're just going to get used to these parametric equations, kind of how they operate today. We're going to do kind of the exact same process, but for this new set of parametrics. Let's try, they don't really give us a range or of t values to use, but if you notice how the t's are in the denominators, we probably can't have a t value less than -1. So when it comes time to develop your table, we can really use any t-value we want as long as it's not -1 or smaller. So what are some t-values you want to test? Some points in time. You think 0 would be easy? Okay, now we're going to try to do this one by hand as well. So let's kind of be strategic on which t's we pick. Since we're dealing with a square root, it might be nice if we can take the square root of an easy number. So perhaps 3 would be another good one to pick because we could figure out the square root of 4. And then 8 would be another easy one. And 15. All right, can we get that table? Let's go ahead and we'll plot those points. Looks like our x's go up to 1. And then the y's, if you look at them, they're getting closer and closer to 1, but not exactly equaling it. So maybe we'll go up to 1 as well there. So at time 0, we're at 1, 0. At time 3, we're at 1/2 and 3/4. And then 1/3 and 8/9, 1/4 and 15/16. So it looks like we're starting at 1 and we're going up this way. We can use arrows if we want to signify that direction. Are we ever going to reach 1 though? If you look at your y column, does it ever seem like you'll equal 1? Not quite. So we're getting closer and closer to 1, but we're not actually equaling it. So maybe we'll put some type of hole there. It's not necessarily an asymptote because you don't have that drastic like shooting up or shooting down motion. You're getting closer and closer to it, but not actually equaling it, so a hole might be a better option. Okay, let's say we wanted to check it on our calculator just to make sure we had the right shape. So in y equals, we'll go ahead and type in the two parametric functions, 1 over the square root of t plus 1. And then for the y equation, we had t divided by t plus 1. Make sure you put it in parentheses. Let's go ahead and hit window. Now we will have to change kind of the x's and y's here. So we chose the lowest t-min to be 0. And our highest one I think we did was 15. And you want to count by 0.01s? Right. X min was 0, X max was 1, counting by quarters. And then Y min was 0, Y max was 1, counting by quarters. It's calculating a lot of data points. That's why it's getting really, really slow. I say we graphed it pretty accurately though, right? There's how it has that shape. Okay. If that's going too slow for you, you can always do second quit, or wait, hit the on button. I think that should stop it from thinking if it's going too slow. Just hit the on button, and you can go back to window and change that t-step. So maybe 0.01 was too small, taking too long to graph it. So we'll change it to 0.1, and notice how that went a little quicker. Okay, but it still has the same shape. Okay, it's really taking its time though to graph that. Okay, let's go ahead and practice eliminating the parameter in this case. Can we choose one of those equations that would be easier to get t all by itself? What do you guys think? Let's do the x one, yeah. Okay, so we'll start with x, and then we want to get the t all by itself, so maybe we'll multiply that square root over. We can divide the x, square both sides, so it'll be 1 over x squared, and then subtract the 1. Alright, so if that's what t is, we can substitute that value in for both t's in the y equation. And maybe we can simplify this a little bit. We'll have 1 over x squared minus 1 up top, but notice how the minus 1 plus 1 down below will cancel. And we'll have 1 over x squared in the denominator. Instead of dividing by a fraction, you can multiply by its reciprocal. So if you were to multiply the whole top by just x squared, 1 over x squared times x squared would change to 1 because the x squareds would cancel, and then we'd have minus 1 times x squared, which would just be x squared. So there's kind of a cleaned up version of your equation with no more t's in it. And if you take a look at this shape, doesn't this kind of look like an upside down parabola, a negative x squared, specifically at a height of 1 on the y-axis, starting up there? So whenever you eliminate the parameter, the rectangular equation with x's and y's in it should generally make sense with the graph that you formed from the parametrics. Because they're essentially the same thing, it's just that these are representing x and y differently, whereas this one is representing them together as a coordinate system. Okay, let's go ahead and try another one. Just getting used to parametrics. We're going to check out a trig one though. Alright, so since we're dealing with trig, what are some kind of easy time values from the unit circle that we might be able to substitute in? What are kind of the easy radian spots on the unit circle? 2 pi, yep. Pi over, okay, so you're doing the quarters. That's okay. You could do pi over 2, or you can do pi over 4, pi over 2, pi, 3 pi over 4, 3 pi over 2, 2 pi. If you don't do quarter marks, you can. Alright, let's see, if we plug in 0, cosine of 0 is 1, so we're left with 2 plus 3, which is 5. And then sine of 0 is 0, so we're just left with negative 1. Let's see, for the next one, pi over 2, cosine would be 0, So we're left with just 2. And then sine of pi over 2 is 1. So negative 1 plus 2 would be 1. Cosine of pi is negative 1. So 2 minus 3 is negative 1. Sine of pi is 0. So we're left with negative 1 there too. Cosine of 3 pi over 2 is 0. So we're left with 2. Sine of 3 pi over 2 is negative 1. So negative 1 minus 2 would be negative 3. And then 2 pi, we're back at that beginning spot on the unit circle, so we should have the same as 0. Alright, so on the x-axis, we have to go out to negative 1, but then out to 5. And then on the y-axis, up to 1, but down to negative 3. Alright, so let's plot some points. 5, negative 1, 2, 1, negative 1, negative 1, 2, negative 3, 5, negative 1. So we're back at the start. What do you think it's going to look like? Perhaps, okay. If you were to connect them rigidly, like in straight lines, it would be a diamond. If we had more data points, it'd be a little bit more obvious to see it, but we're actually going to have some type of ellipse, right? It's like a football shape, okay? And since we know the path, because we started at this point and we went around the ellipse, maybe we can throw in some arrows. Okay, now we can tackle the equation kind of 2 different ways. If you're familiar with writing the equation of an ellipse, we should be able to just look at this ellipse right now and we can figure out the equation. Or we can go ahead and try to eliminate the parameter using some algebra. Now, we're going to do it both ways just so you can see the connection. But let's go ahead and talk about what the equation for an ellipse kind of looks like. It's this weird fraction looking setup. And we need to somehow figure out where the center is and what the kind of 2 radii are from the center, like to the closest point and the farthest point. So based off of how we drew that, can you identify where the center might be, the ordered pair? If you were to put a dot in the center, where does it kind of look like it would be? 2, negative 1, yeah, I'd say somewhere right there. So since you went 2 to the right from the origin, you would have x minus 2, kind of the opposite of what's actually going on. And since you went down 1 from the x-axis, you would have y plus 1. Again, kind of the opposite of what is actually happening here. So you have 2 different radii that you can measure. You can go from the center to the closest point, or from the center to the furthest point. So this distance is 2 units. This distance is 3 units. Notice how the horizontal radii is 3. So underneath the x variable, which is a horizontal variable, we would actually put 9. That's the squared of that value. And then the vertical radii is 2. So under the y variable, we would have 4. So that's just a standard way, if you're familiar with the setup of an equation, to write the equation of an ellipse based off of the center and the 2 radii. But we're going to try to create the same thing by eliminating the parameter. And this is when it's going to get a little tricky, because since we're dealing with trig functions, we're going to utilize a trig identity. Do you guys remember sine squared plus cosine squared? What that equals? 1. Good. Okay, so we're going to utilize that. So with this maybe we'll work with the x equation first. If you were to get the cosine all by itself, we would subtract the 2 and then divide the 3. So we'd have x minus 2 over 3 equals cosine of t. If we were to do the same thing for the y equation, we would add the 1 and divide the 2. I think we can do that, right? Now, based off of this trig identity, we need to do sine squared plus cosine squared, and that would equal 1. If cosine of t is this fraction, if we square cosine, we'd have to square that side as well, right? What you do to one side, you do to the other. If we did the same thing here, if we square sine, we have to square the other side as well. Do you kind of see it taking shape a little bit? So when we're working with the cosine squared function, we can rewrite that as x minus 2 squared, okay, just the top squared, and then the bottom would be 3 squared, which we know is 9. And if we add the sine squared value, that would be y plus 1 squared over 2 squared, which is 4. And since we added cosine squared plus sine squared, we know the result should be 1. Okay, cosine squared plus sine squared is 1. So notice how we get the same equation by eliminating the parameter. Okay, that one's a little tricky because it was trig. We had to utilize that identity. Are we kind of familiar with parametrics? Getting used to them? They're just two separate equations. Okay, tomorrow we'll get into the calculus of them, like derivatives and how those work.